Chapter 5, chemical bonding. We finished off chapter 4 with naming compounds, I believe. Let's see. Yeah. Yeah, we name compounds. Now we're going to take a closer look at the covalent bond. Covalent bond, remember what that is? Where the atoms share electrons, right? As opposed to ionic bond, where they donate their electrons from one to the other atom. And then what holds them together? Electrostatic charge. That's all there is to it. But sharing is a little bit different. And where do you find elements that share electrons? If you have two elements from which side of the periodic table? Nonmetals. Nonmetals share electrons, because neither one has enough pull to take the electrons from the other. So they more or less have to share. Okay. That's just the outline. We'll get to all that stuff eventually. All right, we mentioned this before. Ionic bonds form between metal and a non-metal. Ionic bonds involve electron transfer. Ionic compounds do not contain discrete molecules. In other words, they don't have collections of atoms that behave as a single unit. They form more of a crystal lattice, we call it, where you have positives and negatives distributed in an orderly fashion. So when we write ionic compounds, we have to write the simplest whole number ratio of the ions, the cations and the anions, together as an expression of the ratio of charges. All ionic compounds are solid at room temperature. Covalent compounds, though, can be solid, liquid, or gas. When an ionic compound goes into solution, it breaks apart into individual ions, which means it can conduct, the solution can conduct electricity. It's an electrolyte. Whereas covalent compounds, not always, but usually don't conduct electricity. There are some exceptions. But in any event, if you have a covalent compound that goes into solution, if it's going to conduct electricity, some part of that molecule has to break off as an ion. Otherwise, there's no route for the charge to transfer through the solution. But fortunately, they're not that common. Okay, so chemical bond that where you share electrons is a covalent bond. And here's an example, an artist's rendition of two hydrogen atoms sharing their one electron each. And the blue is an expression of kind of the region where you might find the electron. It's a funny thing about electrons. We think of them, at least in the beginning, when you're first introduced to chemistry, you might think of an electron as a particle. And sometimes you can treat it as a particle, but other times it's more like a wave. So and that's the modern interpretation of what an electron is it's a wave function. So this blue area that you see there is a representation of where the highest probability of finding the electron is in that region. So when the two electrons come together, you get a redistribution of electron density or probabilities where you might find the electrons. And notice that when they come together and form a bond, most of this side of the probability shrinks in toward the atom. and you get most of your probability between the atoms in a covalent bond. And this is one of the diatomic elements. If you look at your periodic table, the one that I gave you with the blue highlighting, the ones that have the blue highlight are diatomic elements. So under these conditions, 1 atmosphere pressure and basically room temperature, they're going to be in that form. You always have 2 hydrogens connected as a covalent compound. Nitrogen's the same way. Oxygen, fluorine, chlorine, bromine, iodine, all of those are diatomics. Let's see. Okay, so when we write them, at least in the beginning, we'll write them like that. So the 2 electrons are shared between the 2 atoms. But for convenience, sooner or later, we're going to switch to that and just write a single line for the bond. And if you see a single line, that's 2 electrons. If you happen to see, say, oxygen, if you see 2 lines, that's 2 pairs of electrons, or 4 electrons shared between the 2. Okay, nitrogen has 3 pairs of electrons between. That's why nitrogen is so stable, because the more bonds you have, the stronger the connection. All right. So we did introduce Lewis structures, didn't we? I'm pretty sure we did. How to draw a Lewis structure. May need a refresher. It has been a whole week. So with the 2 hydrogens, the only electrons they have available are in the bond. Right? There's only 1 electron per hydrogen. So you don't see any extra electrons around either of the hydrogens. But when you bond hydrogen and fluorine, if we draw, this one has 1 electron, fluorine has 7 electrons. Right? You look at your periodic table, it's from the left to the right, it's 7 groups over. If you have to skip the transition metals to get there. But that tells you that it has 7 electrons in its valence shell. These 2 can be considered paired, and they don't want to bond with anybody. But this one is unpaired, and it's free to bond. So you form a bond with 1 from one side and 1 from the other, and that's why it looks like that. If you have 2 fluorines, then just substitute a fluorine here with its electrons, and it still has that 1 free electron. You have 1 here, 1 there. That forms a bond. So it's a single bond in all of those. Bromine, we write, now bromine is 2 periods down from fluorine. So it has a lot more electrons in there, but most of them are core electrons. The only ones that are involved in bonding, the valence electrons, would be the same for bromine as for fluorine. You have 7 in the outermost shell with 1 available to bond. So bromine is going to look, in a Lewis diagram, it's going to look like fluorine because it's in the same group as fluorine. And it can only form 1 bond. Okay, these others, these are called bonding pairs. When you have a single line between them, that's 1 bonding pair. Or you can have a double bond, 2 bonding pairs, or 3 bonding pairs. I've never seen 4. But we need to name everything, right? So these are non-bonding pairs. And electrons like to be paired. It's a funny thing. Even though they're they're negative charge and you would think they'd repel one another, they tend to pair up when they can. And then if you leave anything out, the unpaired electrons are the ones that are available for bonding usually. Now we can dig into these valence electrons later if we need to. But you have the bonding electrons, you have the non-bonding electrons, and the electrons that are unshared, those pairs that are unshared are often called lone electron pairs. They're all alone out there, nobody to bond with. Okay, so this is a single bond. Just one line means 2 electrons. All right, carbon dioxide, you have a double bond on either side of the carbon. So what does that tell you about carbon? Well, if we're sharing equally, and we know we've got an oxygen over here and an oxygen there, and we've got 2 between them, then these representative elements tend to form, share electrons in such a way that they think they have an octet, right? 8 electrons, right? So you can say this, that. 2, 4, 6, 8. Oh, excuse me. My mistake. 2, 4, 6, 8 around that oxygen. 2, 4, 6, 8. Okay, so oxygen thinks it has an octet. Carbon thinks it has an octet too, 2, 4, 6, 8. But carbon comes into the bonding process with only 4 electrons. And oxygen comes in with only 6. So it has 2, 4, like this. There. So it has this one unpaired, that one unpaired, these lone pairs, and then do like that, you get 2 bonds. You go on the other side with an oxygen, you can pair off these 2 also. So when we look at it from Lewis' standpoint, this makes perfect sense. Okay, so those are double bonds, and you can also have triple bonds. So let's look at nitrogen. Nitrogen is in the 5th column to the right. So it has 5 valence electrons, right? Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so these are unpaired electrons. There's one lone pair, one lone pair. You can form a bond between these 2, between these 2, and between these 2. So there's your triple bond. And we can do this logically with just Lewis diagrams. Now that one, I guess it's passable, but it's missing its lone pairs, right? If we drew a Lewis dot structure for that, it needs these 2 over here and these 2 over here to be complete, right? How many electrons are shared in a double covalent bond? A double bond? 4, yeah. 2 pairs, 4 electrons. All right. Over time, you may find this trend yourself, but it might be easier just to give it to you and let you discover that it's true later. Atoms of non-metallic elements have a tendency to form a specific number of covalent bonds. And I've shown you why, because if you draw the Lewis dot structure, you see which are unpaired and which are paired. And by the way, how did I know to put them in those positions? Well, let's see, what was it, 5? You just start and go clockwise or counterclockwise, it doesn't matter. 1, 2, 3, 4. Then you start pairing them up. Okay, that's how you determine which ones are paired and which ones are unpaired. You go around singles first and then start pairing. Some of you may have caught that, but I think I better emphasize that point. So the number of bonds that can be formed is equal to the number of electrons that this atom has to share to make an octet. So if it has 5, in order to make an octet, it needs 3 more, right? So it needs 3 more bonds to make an octet. And it donates one of its electrons and gets one from the other side and makes a bond. So oxygen tends to form 2 bonds, either 2 single bonds or a 1 double bond. We've seen the 1 double bond already. Perfect example of 2 single bonds is water. Right? You've probably seen this more than you want to. There you go. And those are the ones, the valence electrons that weren't used. Right? Oxygen is in the 6th column, so it has 6 electrons, 2, 4, 5, 6, and then it gets 1 from here, 7, 1 from here is 8. That's oxygen, water. Nitrogen tends to form 3 bonds, right? We've seen why. It's either 3 single bonds, a single and a double, or a triple bond. As long as it's got those 3 bonds, it thinks it has an octet. Carbon, on the other hand, forms 4 bonds because it has 4 valence electrons that are unpaired. So it can form 4 single bonds, form a double and 2 singles. It can form a triple and a single, or 2 doubles. And it has its octet. That's probably why you can make so many different compounds using carbon. And we keep organic chemists in business for centuries. Okay, oxygen can form 2 covalent bonds. All right, there's one type of covalent bond that's a little odd. Up to this point, we've shared electrons. In other words, when you form a bond, 1 electron from one atom, 1 electron from the other atom. But sometimes bonds form, and the only way we can explain them is by saying that one atom comes in and takes 2 electrons from the other atom and forms a bond. This is called a coordinate covalent bond. Now, once the bond forms, there's no way to tell where the electrons came from. But if you know the chemistry, how the bond formed between this side and that side, then the only explanation for it is that one atom came in and stole 2 electrons from the other one. Well, it borrowed them and formed the bond. Here's an example. This HOCl. Let's see, that's, well, if we put it in solution, that would be hypochlorous acid. Because this would be the hypochlorite and a polyatomic ion. We add a hydrogen to it, makes an acid. As long as you put it in water. And this reaction probably occurs in water. But you can also bring in in order to understand what's going on, you have to draw the Lewis dot structures. Right? there. So that one has its duet. That's 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for chlorine. So that molecule is perfectly happy the way it is. All the octets are satisfied. But if you bring in a reactive oxygen, and normally we would draw the oxygen like this: 1, 2, 3, 4, 5, 6. And we have 2 of these electrons reactive. But there are no players over here, right? They're all paired. So what we do is take that one out, put it here, and then this one provides both electrons for the bond. That's a coordinate covalent bond. Okay. And there's no way to tell. After the bonds form, there's no way to tell where the electrons came from. We just have to deduce it from the reaction itself. Okay. I'm not going to spend a lot of time on this slide. I don't know how I put it in there. It's just an artist's idea of the difference between the regular covalent bond and the coordinate covalent bond. Right? It gives you an idea of, for one, the electrons are donated from both sides, and the other one, both electrons come from one side. Oh, we have another example. Do we need to talk about that? Nitrous oxide is like that. Nitrous oxide, everybody knows nitrous oxide, right? You ever been to the dentist? You use gas at the dentist? Okay, then you breathe this stuff. That's laughing gas. We call it nitrous oxide because that's sort of grandfathered in. If we named it by our convention, it's a type 3 compound. So it would be like that. We'd name it what? Dinitrogen monoxide. That's the proper IUPAC name. But it's been around for so long, and the nitrous oxide hit it and stuck. So sometimes you have to know we call them trivial names. Non-standard names are called trivial. I don't think there's any value judgment attached with that. But the nitrogen itself, the dinitrogen, is perfectly stable. Oxygen comes in, just like it did with our previous example, and takes 2 electrons from the nitrogen. Two electrons that used to be over here. Now they're in the bond. Carbon monoxide, which is a really nasty chemical. At least for living systems, it is. So you know how carbon monoxide poisons you? Okay, so you've had some physiology and know what it does, right? It goes in and latches onto your hemoglobin. It won't let oxygen anywhere near it. It will not detach from the hemoglobin, the iron in the hemoglobin, actually. So you actually suffocate at the cellular level. Okay. So the Lewis structures, you can also write Lewis structures for complete molecules. I don't think we did that last week. We just introduced the Lewis structures for individual atoms. Okay. So there's a procedure that is fairly reliable for writing Lewis structures for whole molecules. And the example that's given here is sulfur dioxide. So what do? Well, first, you know that the compound exists. that covalent compound is verified, it exists. It has to be real for our purposes before you even start to do this. And the Lewis dot structure just helps you organize your how the bonds form and where they're located. So we know that this one is real. Okay, so what do you do first? You count up the valence electrons for all the atoms in the molecule. Sulfur and oxygen are from the same family, so they have 6 valence electrons each. So 3 times 6 is 18. Right? That's just the valence electrons. We don't mess with the core electrons. We don't care about them. They're not involved in bonding. So once you do that, then you take the molecule and you form single bonds. Now here's the tricky part. Which one goes in the middle? Do we string them together like SOO? That, I mean, on an aesthetic level, that doesn't make sense. No, we form S and a single bond on either side, like that. Generally speaking, the more electronegative goes in the middle. And what I mean by that is, if you've got a choice between two, and one of them is below and or to the left of the other one, that's the one that goes in the middle. And that's the case here. Sulfur goes in the middle. Now, we've used how many electrons? 2, 4, right? So we got 14 electrons remaining to position. You start from the outside and work your way in. Right? So we say 1, 2, 3, 4, 5, 6. We've used 6 now. 7, 8, 9, 10, 11, 12. We've got 2 electrons left over. Now oxygen has an octet, right? 2, 4, 6, 8, 2, 4, 6, 8. Sulfur does not. Sulfur's only got 4. Okay. So if we put these 2 electrons, now we work our way in, put these 2 electrons on that sulfur. Now sulfur has 6. So how do we make an octet for sulfur without destroying the octet for the other oxygens? We take 2 of these and form a bond right there. Okay, so that gives you that, and that. Two, 4, 6, 8, 2, 4, 6, 8, 2. Oops. 2, 4, 6, 8. Okay, so now we have this molecule is satisfied octets for all of its members. And that's what these subsequent slides tell you to do. Right? It's just one after another, tells you to do that, 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 that. Right? There's the ones where that's where the oxygen donates that pair to make a double bond. And then to be sure, we're supposed to have 18. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so we're good. Now, I may be jumping the gun a little bit, but why didn't we take a pair of electrons from that side and make a double bond? We could have, right? We could have written it like this. Like that. That's a perfectly valid Lewis dot structure. Just go from the other side. That's one of the problems with Lewis dot structure. You can't draw the actual in between. It's all or nothing. So since these are both valid Lewis dot structures, then we have to say, came up with the idea of resonance. So we say these two resonate between each other. I mean, one is not dominant over the other. It could be either one, right? It just goes back and forth. And we put a double barbed arrow in like that. It says it goes like that and resonates between the two. We know from actual measurements that these bonds, this bond and this bond, are equal. They're equivalent in strength and in character. It's not a complete double bond. It's not a complete single bond. It's something in between. Okay. But we can't write it that way for a Lewis dot structure, so we have to come up with resonance. Right. So you can see that for every solution to a problem, there are created 3 or 4 more problems. Okay, so let's draw Lewis dot structures for some others. We did hydrogen already. We did all 3 of those before. We don't need to do those again. All right, there they are, there they are, there they are. Yeah, let's try something else. How about ammonia, NH3, ammonia. Okay. So how many valence electrons do we have? Let's see. Nitrogen is in the 5th group. It has 5. It's 5 here, and then 1 for each hydrogen. So we have 8 total. Which one goes in the middle? Well, hydrogen's kind of funny, right? It's usually the outlier anyway, so the decision is easy. Nitrogen goes in the middle. So we form a single bond with each hydrogen, right? So we have 2, 4, 6. We have 2 electrons. Hydrogen can't take any more, right? It's already got its duet, 2, 2, 2. So the last 2 electrons have to go on nitrogen. And that's our Lewis dot structure for ammonia. Okay. Should be a picture. There we go. We did carbon dioxide already. Carbon tetrachloride. You ever heard of carbon tetrachloride? No. Used to be a dry cleaning fluid. All the dry cleaners used carbon tetrachloride to clean your clothes, your fine clothes. It's very effective and very cheap. But OSHA, Occupational Safety and Health Administration, and the EPA, Environmental Protection Administration, decided that carbon tetrachloride was too dangerous. They had some evidence to believe that. I mean, workers in the industry were getting sick, and they surmised that it was lifelong exposure to carbon tetrachloride fumes. So they said, you got to get rid of it. You need something, substitute something that's less volatile, less toxic. So now that's why it costs you more to dry clean your clothes than it used to. But remember what we said about carbon. Well, let's do it the usual way. And then I'll introduce the other thought. Okay, so carbon has 4, right? It's in the 4th group. Chlorine is halogen, so it has 7, right? 4 times 7 is 28. So we have 32 electrons that we need to deal with. All right, which one goes in the middle? Carbon. Carbon's to the left of chlorine. So we have carbon. And 1 bond for each chlorine. 2, 4, 6, 8. Okay, so we have 24 electrons we have to position. Now, we could go round and round and round, or we could say, how many does each chlorine need to make an octet? Right, it's already got 2, so it needs 6 more, right? So 6 12, 18, 24. There we go. That's carbon tetrachloride. We've used up all of our electrons. And everybody's got an octet. Chlorine's got an octet. Carbon's got an octet. What I was referring to earlier was, remember we said carbon tends to form 4 bonds. Right? So we could just put carbon up there, form the 4 bonds, slap in the chlorines, and fill in the electrons. Fill in the electrons to make an octet for everybody. And then it's probably a good idea to count them up too. See if you didn't create matter or destroy matter in the process. What's the total number of dots in the Lewis structure for SO2? The total number of dots in the structure. Remember our structure for SO2? We'll just do the first one we did. Right? 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons. So the total number of dots is 2, 4, 6, 8, 10, 12. 12 unbonded pairs. Wait a minute. Oh, okay, I see what they're doing. They're saying we turn these into dots. So they should have said total number of electrons. Right? Because when you write it this way, you think the dots are only the unbonded pairs. Okay, I need to do some editing on this one. Okay, so we've learned how to name compounds using polyatomic ions, but polyatomic ions are covalently bound units that just happen to have a charge. So the trick for polyatomic ions is, what do you do with that charge, right, when you start to draw the Lewis structure? And that's what we're going to do next. So for K2SO4, right, let's name it first. Okay. Recognize the polyatomic right here? Sulfate. Right. Yeah, you might have to look it up. Sulfate. It has a 2- charge, and potassium has a 1+ charge, so we need 2 of them to balance the charges, right? Okay. But these 2 parts are ionically bound. In other words, this potassium and that potassium are on either side of the sulfate, which has a 2- charge for the whole thing. Okay, so that shows you the, let's see, now they put brackets around this one too. Be consistent. Okay, on the inside is our covalent compound, covalent polyatomic ion. Okay, that goes on the inside. That shows you that the covalent's here and the ionic is there. It's kind of a mix. So let's look at this part and write the Lewis structure for this. Okay, how many electrons do we have to deal with? Sulfur and oxygen are both from the same family. They have 6 electrons each, right? So that's 4 + 1 is 5. 5 times 6 is 30. So we have 30 electrons from here, but we have 2 extras. So that's the total number of electrons we have to position in our Lewis dot structure. Okay? All right, so which one goes in the middle? Sulfur, right? It's below oxygen. So sulfur, and then we position our oxygens like that, 2, 4, 6, 8. 24 electrons left, okay? We can do the carbon tetrachloride was a good example, right? We have 24 electrons left. How many does each oxygen need to make an octet? This many. 6. 6 times 4 is 24, isn't it? Okay. Everybody's got an octet. Plus, now it's complete. Without the charge on that group, it's not complete. So that would go right there. Okay? And that's what the picture shows. Okay, how many valence electrons are present in SO4 2 minus? Well, we counted them up. 32. I should have put that slide first. Okay. Now we're going to use this information to try to get a picture of what these molecules look like in 3 dimensions. Their molecular geometry. We're going to keep it real simple because this is one of those chemistry topics that can get complicated real fast. So why would we want to know the geometry of a molecule? No speculations. One thing is, if you know the geometry and you know the nature of the bonds, you can say something about the overall electron distribution in the molecule. That's as simple as I can put it. Because every atom in that molecule has a draw, an electronegativity, a draw on the electrons that are in the bond and in the lone pairs. And if you have an element in there that's drawing really strong on the electrons, but not enough to make an ion, it doesn't destroy the bond, then that tends to distribute electrons to one side of the molecule. And what does that leave behind? A positive imbalance. So you get a polarity in the molecule. You get a slight redistribution of electrons to one side, and you leave behind positive on the other side, and you get a polar molecule. And that contributes to the molecule's behavior, how it reacts with its identical neighbors, or how it reacts to any other molecules that you try to mix in with it, say in a solution. Knowing the 3-dimensional arrangement of atoms in a molecule, especially when they get really big, but we're not going to go there. You can say something about their reactivity, especially for biochemicals. When you know the shape of the molecule, you can say something about how it reacts with, say it's an enzyme. You have the enzyme and you have the substrate, the molecule that it works on it. Okay. Has anybody been introduced to that idea yet? Okay. Just grasping at straws here. So the shape of the molecule has an impact on how the molecule reacts when it encounters other molecules. All right. So in order to do that, we're going to use this theory called VSEPR. All right. VSEPR is short for valence shell. Valence shell. VSE electron pair repulsion. What that means is, once you've drawn the Lewis structure, which is the first step, then you know where all the electrons are. And this model says that what you want to do to say something about its three-dimensional structure is you got these electrons that are lone pairs and in the bonds, and you say they try to stay as far away from each other as possible. That's the electron pair repulsion. And you go to the closest regular geometry that will give you that minimized repulsion, where they're as far apart from one another as you can get. Okay. Now, I think this thing was named by someone and it stuck because it's not always just the electron pairs. Sometimes you consider it electron groups. And I'll show you what I mean by that in just a minute. Okay. Rather than talk about it, let's see if we can get to an example. Okay, steps. Draw the Lewis structure. So you need to get comfortable with drawing Lewis structures. And there are probably a whole bunch of them in the back of that chapter that you can practice with. Then you count the number of electron groups present around a central atom. And we're going to try to keep it real simple so that we only have one central atom. You can use VSEPR model for larger molecules, and you say this atom's got this many groups around it, so it has that shape. But over here, this one's got a different number around it, so it has a different shape. Right? So you can get multiple geometries within the same molecule if it's big enough. But we're going to try to keep it simple. Right? Simple molecules, only one central atom for now. And then try to get comfortable with deriving the three-dimensional structure based upon the Lewis dot structure for the molecule. Okay. So then, first thing you have to do is, once you've determined the number of electron groups around the central atom, you deduce an electronic geometry. That is, how do the electrons distribute one another? They could be lone pairs, or they could be in bonds. They could be bonding pairs. Once you determine that, then you cover up the lone pairs and say, all right, what is the true molecular geometry? Because you're not going to see the electron, the lone pairs anyway. If you could get down small enough and look at the molecule, you just see the atoms and their shape. So we got to go through the electronic geometry first, then we can deduce the molecular geometry afterwards. That's where we're going with that. Okay, here's an example. We got two possibilities here. Well, two molecules, carbon dioxide, and we drew the structure for carbon dioxide before. And you look at the central atom, which is carbon. How many electron groups surround the carbon? Well, it's got one on the right-hand side, one on the left-hand side. Right? Not just pairs, groups. So double bond, triple bond, they count as a single group. So in this case, you have one on this side and one on that side. So around that carbon, you have two electron groups. And when you have two electron groups around the central atom, the most efficient and the least repulsive arrangement is linear. Right? Put them on opposite sides of the molecule, they have the least possible interaction. Okay? Same thing for this one. Hydrogen cyanide. Right? That's a nasty molecule too. If you ever want to get rid of a spouse or a partner. That'll do it. Though I think it leaves traces though. So these are both linear molecules because you've got a group here and a group there, and they're repulsive. The electrons repel one another to the maximum extent, makes it linear. Okay, that was fairly easy to see. Let's get more complicated. How about formaldehyde? Formaldehyde, H2CO. This is the Lewis dot structure for formaldehyde. Well, around the central atom, you have a hydrogen here, a hydrogen there, and an oxygen there. So you have 1, 2, 3 groups. The most efficient arrangement for 3 groups is what we call trigonal planar. It's basically an isosceles triangle. Okay, and they're all in the same plane. If they move out of that plane, then they feel more repulsion from the other groups. So this is the logical arrangement. This one is sulfur dioxide. Remember, sulfur had a lone pair on it when we drew that earlier. Right? So you got this 1 group, 2, 3 groups. So the electronic configuration is also trigonal planar. But the molecular configuration, you just cover that up. What do you got left? The actual molecule is angular. I prefer the term bent, but your book refers to it as angular. And that's what water looks like. Right? If we draw water, right? 1, 2, 3, 4. So water has 4 electron groups. So what's the most efficient arrangement for 4? A regular geometric structure. You may not remember this. Everybody have geometry? That's not the answer I was looking for. The most efficient arrangement of 4 of these groups is a tetrahedron. Right? So you have, say, a hydrogen positioned here, and a hydrogen positioned there, and the lone pair here and the lone pair there. Right? That minimizes the repulsive effect. Well, if you cover those 2 up, what do you have left over? Well, oxygen's in the middle. So the shape of the molecule is like that. It's bent. Now, one of the problems, the most annoying problem, I think, for most students, at least it was for me too, was when we say the geometry of the molecule is a tetrahedron, that's just the arrangement in space of those groups. So you have a group here, group here, group here, group here. That arrangement is a tetrahedron. But then you got to transfer that to thinking about the actual molecule. And the molecule is based upon bonds. And these bonds have nothing to do with the tetrahedron. I mean, well, they're there, right? But they're not a tetrahedron, right? You don't have a bond here like that, the bond over here like that. I don't know if that helps or not. My guess is it didn't help much. Okay, so that's probably the next slide, the tetrahedron. Yeah. So CH4 is the first one. Methane, right? Everybody knows methane. If you have natural gas coming into your house, it's mostly methane. They put a little bit of some of them are captan. Has sulfur in it because you can't smell methane. So we put a little, we dope it with just a tiny amount of sulfur, so if you have a leak, you can smell it. Yeah. And if you had a leak say you've got a vacation home and you haven't been there in 6 months and it uses gas, you have a slow leak, it accumulates gas in your house, probably in the basement. Then when you go into the home after 6 months, you may not smell the sulfur because it could have dissipated, but there's still enough gas in there, and all you need to do is flip the light switch and bang.
My husband was telling me though that they put something in the gas so you would smell it when you have a leak. I didn't know that.
Yeah. We have a cardiologist in Beckley, Dr. Karam, who had a second home down in North Carolina somewhere. I think it was around Charlotte. And he and his wife had been to Ohio to visit their grandkids, and they came back through Charlotte and opened the house up. And he went one side of the house and she went the other side, and she flipped the switch and the place blew up. She died, and he was badly injured. But they didn't smell it because they'd been gone for so long, and the sulfur compound had dissipated. So there it is. So my house is all electric. I'd rather be electrocuted than blown up, I think. Anyway, so methane, you have 4 groups around it, 4 hydrogens, 4 groups, tetrahedron. That's also the molecular geometry because we don't have any lone pairs. Ammonia has 1 lone pair. So the electronic geometry is tetrahedral, but if you cover up that lone pair, what do you got left? You got a pyramid with a triangular base, a trigonal pyramid. Okay. And then the water molecule, we've already done that one. You get a bent molecule. So what does that do for the character of the molecules? Well, for this one, even if there is some polarity in the bond, they're equally distributed around that tetrahedron, so they cancel one another out. So methane is nonpolar. It doesn't have an uneven distribution of electrons. Whereas ammonia has a difference between the nitrogen and the hydrogen. So the nitrogen pulls on electrons stronger than the hydrogen. Plus it has that lone pair out there. So this side of the molecule is slightly negative and this side is slightly positive. So ammonia is slightly polar. Water is very polar. It has these 2 lone pairs out here. Plus, oxygen is more electronegative than hydrogen, and it pulls on the electron density. And this side of the molecule is very negative, but not charged, just very negative. And this side is positive. So that's why at 1 atmosphere pressure and room temperature, water is a liquid and not a gas. If it were nonpolar, say if it were a linear molecule, it'd be nonpolar, and all the water that we normally see as a liquid would be gaseous, and we'd be in huge trouble because it'd all evaporate out of our bodies and we'd just all expire. Okay. So this is what I was mentioning earlier. You can have different geometries around different central atoms in a molecule. All right, so acetylene is that first one. You know, that's the cutting torch gas. As it turns out, both of those carbons have the same number of groups around each one, so they have the same geometry, right? They're both linear. So the whole molecule is linear because they're linear to one another. It's like if A equals B and B equals C, then A equals C. So the whole molecule is linear. Hydrogen peroxide is a little different, right? One side of the molecule over here, right, on that side, would look like water, right? It would have these 2 would be bonds, and these 2 would be lone pairs and form the tetrahedron. Then you cover up the lone pairs and you have a bent. So this side would be bent and this side would be bent. So hydrogen peroxide would look like this. All right, so there's one band and there's the other band. And you would have the lone pairs over here. Okay. Hydrogen peroxide. Hydrogen azide would be a little bit different, right? The nitrogen, the central nitrogen on the right is linear geometry. Central on the left is angular. Why? I'd say 1, 2, 3. Excuse me. 1, 2. Here we go. I left that one out. And this one, there we go. Okay, so this one is going to be linear. Right, it's only got 2 groups. That's it. This one has 3. So what's 3 mean to electronic geometry? It means trigonal planar. But if you cover up that lone pair, now it's bent. Now let me see. I don't want to steal my own thunder. Let me see if I put. Yeah, got some pictures. How are we doing on time? Let me do it this way. Let's see, do we have any more? Let's see what's coming next. All right. That shows you what I was trying to show you on the board. All right. So you can draw yourself a chart and you can say the electron groups are over here. Right. So you can have 2 groups around a central atom. You can have 3, 4, 5, 6. I think that's as high as we're going to go. And then you can have the electronic geometry here. Okay, so if you have 2 groups around the central atom, it's going to be linear. That's the most efficient arrangement. If you have 3, it's going to be trigonal planar. If you have 4, dead silence. It's tetrahedral. Okay. If you have 5, we haven't looked at that one yet. What do you do with 5 groups? Well, the most efficient arrangement is for your central atom, is in here, is to arrange like that. You have 3 in this planar around the central atom, and then you have 2 up here like that. So 1, 2, 3, 4. Well, what does that look like? Well, it looks like a trigonal base pyramid. So we call it this, trigonal did I write that right? Trigonal bipyramidal. It's a trigonal bipyramid. So you have a trigonal pyramid with the base, both of them have bases together. So you have trigonal this way and trigonal that way. There's trigonal here, and then you have pyramid this way, pyramid that way. Trigonal bipyramid. And the last one, and this is electronic geometry, right? We haven't said anything about molecular geometry yet, at least in this context. So if you have 6, how do you get 6 in there? Well, you use this model, and instead of, there's your central atom, you have a square base, and then you have a square base pyramid, 2 of them back to back. Well, what that is actually is, if you look at how many sides there are to that pyramid, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, octahedron, 8 sides, right? Hedron is geometry for sides, isn't it? Yeah, take my word for it. All right, so the octahedron is the best arrangement for 6. And that's where we're going to stop. Now, where do you go from here to molecular geometry? Well, for linear, there's only one choice, right? It has to be linear. No other choice. If you have one lone pair, then the central atom to the remaining atom is still linear. Right? So that was the easiest one. Trigonal planar, right? What if you have one lone pair in a trigonal planar? What does that mean for the others? Well, if there's a central atom here, and you got a bond here and a bond here, but a lone pair there and there, what's that? That's bent, isn't it? Oops, bent. For one lone pair. Well, if you have 2 pair, you're back to linear, right? How about tetrahedral? Well, of course, now this is if you have lone pairs, right? Of course, if these are all bonded pairs, then that's the structure of the molecular geometry. So we don't have to write that one again. But if you have one lone pair for tetrahedron, what do you have? Like ammonia, you have a trigonal pyramid, right? So one pair for this one is a trigonal pyramid. How about 2 lone pairs? Bent, right? Water, bent. 3 lone pairs, you're back to linear, so we won't put that one up there. How about trigonal bipyramid? This one gets a little trickier. So there's your trigonal bipyramid. Let's see if we've got, did I put one in? Yeah. This group on the left, this is for the tetrahedron. This is for the trigonal bipyramid, right? So if you have every position occupied with an atom, it's still trigonal pyramid. If you have one lone pair, and this has been confirmed by laboratory experiment, the lone pair tends to be in this region here. So this lone pair means that you've got the atoms arranged this way. And if you turn it on its side, it looks like a seesaw. Okay. If you have 2 lone pairs, they tend to be in this region also. And now you have a T shape. Now, logic would have it. How would you get the electrons farthest apart? Remember, when electrons are not in a bonding arrangement, what do they tend to do? Right? The bonding confines them. If they're not bonded, they tend to go, they balloon. There's nothing holding them there, right? Except the atom itself. So I would think, logically, that if you had 2 lone pairs, they'd be here and here, farthest apart. But experiment says that they're here. Right, so that's where we have to adjust our theory to match the data. And then if you have 3, they're still situated around here, you're back to linear. Now, what about bond angles? We didn't say anything about bond angles. Most of these are fairly straightforward. In other words, if you have, the bond angle, you need 3 atoms. You need the central atom and then the 2 other atoms. So we go like that and that, that's 90 degrees, right? So bond angle there is 90 degrees. Bond angle here is 180 degrees, right? Okay. How about, let's go back. Trigonal planar. So trigonal planar, what are the internal angles for that? Right. If you go all the way around, how far is it? 360 degrees. Right. So divide 360 by 3, it's 120 degrees. So the bond angle here would be 120 degrees. This one's a little different. The tetrahedral, you just have to learn that one. So the bond angle here in a tetrahedral molecule is 109.5 degrees. It just is. Now, what happens to that bond angle if you have a lone pair here and a lone pair here, and you're bent like a water molecule? Remember what I said about those unbonded pairs? They tend to balloon. Well, if they balloon, they put pressure on the remaining bonds in this molecule. So the bond angle for water would be less than that. It would be kind of squeezed down. I can't remember what it is. Okay. Is it time? No, there's more. There's more. What's the shape of each of the following molecules? Well, HCN. You've only got H, C, and N like that. So around that central, it's got two groups, which is linear, right? Okay. NH3. Okay. We know that one because we drew it like this. Hydrogen here, that's in the back, right there. So our electronic structure would be tetrahedral. Would be a trigonal pyramid, would be the molecular structure. Okay, so linear is always 180 degrees. Trigonal pyramid, notice that it's not 109.5 anymore because this lone pair squeezes these guys down. So it makes it a smaller angle in here. And what's O3? Ozone, right? It depends on where ozone is as to whether it's your friend or not. Right? If it's in the upper atmosphere, it's a good deal because it absorbs ultraviolet radiation. If it's coming out of your laser printer, that's bad because it's very reactive. In fact, there's some water treatment facilities in the world. I don't know if there are any. They might have got rid of them by now. They used to inject ozone into the water stream to kill the microorganisms. It's very effective. Okay, now I've used this term before. Let's talk about electronegativity in earnest. Electronegativity is simply the ability of an atom in a molecule to attract shared electrons toward itself. So that means that if we're going to talk about electronegativity, we have to talk about it in terms of what's its behavior in a bond. So we need sort of a standard. What do we bond it with to determine what its electronegativity is? And that's been a bone of contention for a long time. Several systems have been developed to express electronegativity of each of the atoms so that they can be compared. And they've got periodic tables that have nothing but the symbols and the electronegativities stuck in there so you can see what they are. I think I've got an example here. We'll show it in just a minute. So it's a measure of the relative attraction of electrons toward an atom. Now, for the periodic table, let's see, do I have one? It's coming up. Yeah, okay, that's good enough. The trend works pretty well for the representative elements. In other words, the first 2 columns and the last 6 columns. When you get into the transition elements, things sort of get wavy. But as a general trend, the electronegativity values that we assign to these atoms are smallest in the lower left-hand corner. Like rubidium, I thought cesium's even lower than that. Cesium is lower than that. Down here, cesium. But the highest electronegativity, the strongest pull on electrons for an atom in a bond is fluorine. And these values were proposed by Linus Pauling. And there's a formula that goes with it where you can actually calculate what they are. So he didn't just pull these out of thin air. And this is the most popular system. And it's not so important for the absolute value, but the relative value. So if you have a bond between lithium and fluorine, lithium's 1, fluorine's 4, so you know which way the electrons are going to be pulled. They're going to be pulled toward fluorine. And in fact, they're going to be pulled so strong toward fluorine that you get a complete transfer of electrons to fluorine, and you get an ionic bond. And I'm not sure if I have that listed in here. I guess not. But there's a little chart. What you have to do is just take the electronegativity of 1 and subtract the smaller one and see what's the difference. And if it's above a certain value, you consider it generally ionic. If it's between 2 values, a little less, then has some significant covalent character. And if it's less than a certain value, like if you had sulfur and potassium, it would be 0.4, that would be considered essentially covalent. So those are the ways that we can use this electronegativity value. But the trend is from lower left to upper right is increasing electronegativity. Okay, so that's why metals tend to give up electrons and nonmetals tend to attract electrons. Okay, for this course, that's probably about as deep as we're going to go. Well, I spoke too soon. Why do these trends occur? Well, if you look at the, let's go back. If you go across a period, right? Yeah, that's right. If you go across this period, second period, what's happening? Well, the electrons are in the same energy shell. You're just adding more of them in the same energy shell. But you're also adding a lot more protons. So you're getting this strong effective nuclear charge, we call it. The strong positive charge in the nucleus, but the electrons are not further out. They're basically in that same energy level. So what you're seeing is the effect from left to right is of increased nuclear charge. That's causing the stronger attraction of fluorine than lithium. Okay, that's what this left to right means. Number of protons increase. Now from top to bottom, you see a decrease. So why do you see a decrease? This one's a little more difficult to explain. So as you go down in a group, what's happening? Well, you're adding protons. Yes, that's true. You're getting a higher Z number. But the electrons that you're adding as you go down are in bigger and bigger shells, outer shells. So what you're seeing is that these core electrons are offering a shielding effect against that positive nuclear charge inside. So the outer electrons don't feel it as strongly because they're shielded by the negatives. The positives in the nucleus are shielded by these core electrons. That puts any approaching atom that you're going to compare it with, because of all these extra electrons in the outer shells, they're holding those approaching atoms at greater distance, right? And if you, nobody said physics in here, right? Okay, if you know Faraday's law, it just says that it's kind of like Newton's law of gravitation. The further away you get, the weaker the force. Right? So if you get a positive and a negative charge farther away, then the force is weaker. So if these outer electrons are keeping approaching atoms further from the nucleus, that also decreases the effect. All right. So which one, lithium or fluorine? I already used that example. Fluorine would have the stronger attraction for electrons because it's to the right of lithium. And how about fluorine and iodine? Which has more attraction for electrons? Well, you go up and find that fluorine is above iodine, has a stronger attraction. So you're going to, any bond between those two is going to shift more electrons. The time they spend near the atom is more toward the fluorine. So which one of these has the highest electronegativity? Hydrogen, helium, oxygen, or chlorine? Well, if we look at the periodic table, hydrogen's way over there on the left. Helium is far on the right. Notice in that chart, there are no noble gases in there. We don't even bother with noble gases. Right? They're happy the way they are. I mean, it's kind of, it defeats the whole purpose to try to determine electronegativity for a noble gas. They don't care. So that being said, in this list, we can just discount helium. Then the battle is between oxygen and chlorine. So it's kind of difficult to decide because chlorine is below oxygen. I would think oxygen would have a higher electronegativity. Let's see if I'm right. Yeah. Oxygen has a higher electronegativity than chlorine because it's above chlorine. So now we talk about bond polarity. What do we mean by bond polarity? Well, I did more than hint at it earlier, I think, very beginning. But we have a way of expressing bond polarity. The probability of finding electrons around the more electronegative atom means that the polarity of the bond is going to be toward that atom. And the way we express that, we'll use water again. The way we express the polarity is we draw an arrow like this. And that arrow points toward the negative. And just to be sure we don't get confused, we put a positive on that end. So that means the bond is polar toward oxygen. And the same for this one. Okay? Toward the one with the greater electronegativity determines the polarity of the bond. Another way that we express slight distribution of charge is to use a small Greek letter delta. Right? Everybody knows the big delta, right? But there's another delta, the little d. And this one would be the positive end. This one would be the negative end. Right? Let's balance it. That just means that there's a slight distribution of charge toward the oxygen. Right? We do that. So if we just put a negative up there, you think, oh, well, that's an ion. But no, they're not ions. It's just slight distribution of charge. That's two ways that we express polarity in a bond and in regions of the molecule. Now, if you know anything about, anybody heard of the term vector? Okay, this is a vector. It shows both, well, actually, it's not really a vector. It shows only direction. Vectors show direction and magnitude. So, but if we know the values here, and we say, all right, if we sum them up in a vector sense, we don't just say we add 2 and 2 equals 4. We say, if they're both headed this direction, then overall, the molecule is like that. So the whole molecule now can be said to be polar toward the oxygen side. That's all that means. You don't have to know how to do vector addition. Right? If you never had physics, then it's strange. All right. So that's bond polarity. Now, is this bond going to be polar? No, I don't think so. Because you got two equally matched atoms in that bond. Both of them are hydrogen. They have equal electronegativities. There's absolutely no polarity in that bond. Polar covalent. Here's an example. HCl, hydrogen chloride. Which way is the polarity going to go? Probably toward the chlorine. It should be more electronegative than hydrogen. We can go back and see. Oops, too far. Hydrogen's 2.1 and chlorine is 3. So yeah, it's going to be polar toward chlorine. Chlorine has the higher electronegativity. Let's see, let's go back down. There you go. And that shows the notation that I was using earlier. Oh, we do have it. Yeah, okay. So if you subtract the electronegativities of the two atoms in the bond, and the value is less than 0.4, we say that is a covalent, non-polar covalent bond. Okay. If the difference between the two is between 0.4 and 1.5, we say it's a polar covalent bond. It's still sharing, but the bond is polar. Between 1.5 and 2, difference in the electronegativities, it has characters of both, ionic and polar covalent. And then you have to decide what are the atoms, what are their natures, right? If there's a metal involved, it's probably ionic. If they're two non-metals, then we lean toward the polar covalent. Okay, that's the tiebreaker. If the difference is greater than 2, it doesn't matter. They're ionic. It's an ionic bond. All right. So let me see. I got 20 minutes. How much more material do I have to cover? Ooh. Too much to stop here. Arrange these in descending order of polarity. The first one is easy, right? Because fluorine is a member of each one. right? It's got the maximum polarity. So the most polar will be the one where the atoms are farthest apart. You got nitrogen, oxygen, and carbon. Carbon and fluorine are the farthest apart. It will be the least polar. So it'd be the last one. The next one would be oxygen. And the first one would be nitrogen. Descending order of polarity. Descending order of polarity. Oh yeah, oxygen and fluorine, they're closer together. Did I say that right? Okay. The next one is a little trickier because you got a mix. So carbon and fluorine and silicon and fluorine, we can decide which one of those is more polar than the other one. Carbon and fluorine, silicon is below carbon, so it's going to be more polar. This one's going to be more polar than that one. Now, where does nitrogen and oxygen go? Well, they're right next door to each other, so they're probably the least polar. Descending order. So this will be the last one. This will be first, second, third. There you go. Of course, the last one, chlorine, that's nonpolar. Right? That would have to be the last one. Then you would say boron and chlorine. Okay, versus sulfur and chlorine. Okay, sulfur and chlorine are very close together, so it would be to the farthest right would be chlorine, then sulfur chlorine, and then boron chlorine. So we should BCl first, then SCl, and then ClCl. All right. So to answer this question, which one will be the least polar, yet still polar covalent? So if you're not actually given the values so you can use that chart, then we just sort of have to process of elimination. Polar covalent. All right, which ones are covalent? Magnesium oxygen is not covalent, right? That's a metal nonmetal. So we can throw that one out. Oxygen is covalent, but it's not polar. So we can throw that one out. So that way we only have to deal with carbon, silicon, nitrogen. So which one will be polar covalent, but the least polar covalent? Carbon, oxygen, they're 2 steps away. Silicon, oxygen is more polar. And nitrogen, oxygen, that would be the least polar covalent. I think that's nitrogen, oxygen. Yeah. Did everybody see what I was doing there? Or just kind of, or it happens. Most polar without being considered ionic, right? So we can throw out magnesium and oxygen. Most polar will be the ones farthest from each other, silicon and oxygen. There we go. Okay. So this topic, I've already described that. How do you determine if a molecule is polar? The entire molecule. You need to know 2 things. You need to know bond polarity of all the bonds in the molecule. And then you need to know geometry. Because if you have, say, 2 polar bonds, but they're both opposite directions, they cancel one another out. So carbon dioxide has 2 polar bonds, but it's 180-degree geometry. It's linear. So they cancel one another out, makes carbon dioxide overall a nonpolar molecule. Okay? We used to use carbon dioxide in a device called a supercritical fluid extractor, which just means you put carbon dioxide under enough pressure and it turns into a supercritical fluid, which is, it's kind of like a gas and kind of like a liquid, but not either one. But it's very effective. It penetrates plant tissue very effectively, dissolves almost everything, pulls it out without damaging it, and then it collects it into a container. And then when you release the pressure, carbon dioxide goes gone. You're just left with your extractor. Very efficient. But it's because it's a non-polar molecule, it can pull out all this stuff that's difficult to get at. Okay, so I mentioned that bond polarities and molecular geometry determined. So there you go. Carbon dioxide is a non-polar molecule. I won't beat that horse anymore. Water is a polar molecule. Hydrogen cyanide is a polar molecule. Why? It may be linear, but the polarity of the bonds are additive. See? They're both pointing the same direction. This is polar toward carbon and this one's polar toward nitrogen. So overall, molecule is polar toward nitrogen, even though it's linear. The linear concept only cancels when both of the bonds are equal. In this case, they're not. Okay. Oh, what was the question? Does silicon dioxide contain polar bonds? Is the molecule polar or nonpolar overall? Okay. Oh, we have to do that. Let's see, do I have time? Yeah, we're kind of racing the clock here. I'm gonna have to skip this one. Sorry. Draw the Lewis dot structure, determine the geometry, then say, are the bonds polar? Silicon and oxygen? Yeah, they're polar. Polar toward oxygen. And say, all right, what does the geometry say about overall? Which of these are polar? Well, fluorine is not polar, right? Because you got two of the same atoms. It has to be nonpolar. HF, yeah, that's polar. What do we say? Hydrogen's 2.1 and fluorine is 4. Yeah, that's definitely polar. Ammonia, is that a polar molecule? Yeah, toward nitrogen. And then you got that extra pair of electrons up here. So it's polar toward that lone pair. How about SO2? I think that's a linear molecule. No, it's not. So it'd be polar toward the, polar toward the oxygen. I think oxygen is more polar than sulfur. Sulfur is the central atom. Which of the following? That's polar. That's polar. Yep. Sulfur dioxide polar. How about carbon tetrachloride? Nope. Because the polarity is toward chlorine, right? The electrons move toward chlorine, but it's in a regular tetrahedral shape. They all cancel each other out. Yeah. Critters in the wall. I think that's Vincent next door in the physics lab. Okay. I might have to skip that one. Binary molecular compounds. We talked about this already when we were naming compounds. Yeah, binary molecular compounds. This emphasizes the fact that when you're naming them, the no, wait a minute. Full name of a non-metal of the lower electronegativity. Yes, that's right. That's right. Excuse me. Lower electronegativity comes first. it takes the position. Remember the type 1, type 2, type 3. Type 3, we try to figure out which one comes first because they're not ions. Right? So we take the one that's more metallic, or the lower electronegativity, the one to the left and below is the cation position. Right? So if we had sulfur and oxygen together, sulfur's to the left of oxygen or below oxygen, so it comes first. We say sulfur dioxide. Let's see. There's your prefixes again. Did we have those in the last chapter too? Yeah, the Greek prefixes for the numbers of each one. There's some duplication going on here. Some compounds have common names that we just can't get rid of. Right? We don't say dihydrogen monoxide. unless you've circulated. Did I tell you about that? Years ago, there was a blurb that was circulating about this dangerous chemical called dihydrogen monoxide. And it said it could do this, it could do that, it could do that. Okay, that's water. Peroxides. Any compound that has this, this, and that bonded to something else, that's a peroxide. So you put hydrogens on either side. That's hydrogen peroxide. If you got acne medication at home, then it could have benzoyl peroxide. So there's the benzene, and there's the benzoyl, like that. Oh no, I'm sorry. Excuse me. Like that, and then like this, and then like this, and like this. So these are your benzene rings. There's the peroxide. So when you put it on your skin, the heat from your body breaks that bond right there. It's very weak and makes it into a free radical. Have you ever heard of free radicals before? They say you eat certain types of foods and take certain vitamins, and they scavenge free radicals from your body, because free radicals are very reactive and they'll do damage to your DNA. So when it breaks, one of the electrons from that bond goes here and one of them goes there. A free radical is an unpaired electron, right? They're very reactive. So that's why on your skin, this free radical is out there and it kills the bacteria that cause acne. Panoxyl is a name brand example for something that contains this. But those are peroxides. Ammonia, that's a common name. Hydrazine, N2H4. Methane, ethane, those are actually proper names in organic chemistry. Methane, ethane, propane, butane, pentane. Those are longer and longer hydrocarbons. Okay. Octane, it's in your gas tank. Nitrous oxide, we mentioned that one earlier. Nitric oxide, right? That's all the rage, as they used to say, right? It's supposed to dilate your vessels and provide better blood flow to every part of your body, and you feel more energy if you get nitric oxide. So you eat super beets, or you drink super beets, or you eat their gummies or whatever, and you're supposed to get more nitric oxide in your system. I don't know if it's true. There's supposed to be some research on it that says, yeah, it helps you. Okay, which of the following compounds is named incorrectly? How much time we got left? All right. Nitrogen dioxide. That's right. Because it's two nonmetals. So we just need to say how many there are. Actually, they're all type 3 compounds. Phosphorus pentoxide. Is that right? Diphosphorus pentoxide. Right. Did everybody get a copy of that extra credit? 50 ways to name your compound? Okay. Did I mention, let's see, we covered everything, but what do you do with waters of hydration? Did I mention that one? I didn't. Okay. So if we have a compound that has some water attached to it, but it's not part of the compound, the molecular structure of the compound. Yeah, that's not accurate, but we write the water separately. So if we have copper sulfate, all right, so this is a 2- charge, that's a 2+ charge, but there's some water attached to it. We put a dot in the middle of the line here, and then we say how many of them there are. For every one of these, there are 5 waters attached to it. This is, so that we call this copper 2, right? It's a transition metal, so we have to say it's not one of those that's, yeah, it has more than one charge. Copper 2, sulfate, and then we just say how many waters. Pentahydrate. That's how you name that type of compound. Okay. That should cover everything in the, that's the only one that we hadn't talked about that there's 1 or 2 examples in the extra credit. Okay, so that's the wrong one. The rest of them are right.